Now we'll go over the prerequisites for the final topic of the springs. If you feel that you are familiar with all these topics, you may want to skip. You should study them properly, in the, with examples and details. Here I will go over very quickly on each topic because they are relevant. So let me clean this video, my blackboard. So the first topic is scalar and vector. So this is simple. Vector has magnitude and direction. Scalar has only magnitude. So this is vector and this is scalar. So if you have a fever of 101 degrees, you do not need to mention direction. If you have a block of mass 2.5 kgs, you don't have to say which direction. But if a plane is flying, say from Patna here to Delhi, and imagine that it takes this path. So at any point it is relevant to know that the speed of the plane, say, is 300 kilometers per hour, and it is going in, so if I draw, so this is north, this is west, so you say that is going in northwest direction, because without the direction it doesn't make sense to express velocity of a plane. So velocity is a vector displacement is a vector. So if I draw this axis like this, this is my x direction and this is my y. So 1 meter in this direction is different from 1 meter in this direction when we talk about displacement. So that gives you a good idea of scalar and vector. I'm sure you are very familiar with this. Now, a very important topic of vector multiplication. Vector multiplication. So the first type of multiplication is vector and a constant. So let me draw the axis. This is x, this is y, and I have a force F of magnitude 5 Newton at an angle 30 degrees with the x axis. So I draw this. This is my vector F at an angle 30 degrees with the x-axis. And now I find another vector, call it F prime, and I multiply 0.5 to the original vector. So this was Newton. So magnitude of F prime, this is how we write magnitude, will be 5 divided by multiplied by 5, so 2.5 Newton. And let me choose a different color. So, and let me draw this the new vector parallel to, okay, almost half. So this is your F prime. So the magnitude is half of the original force, direction is the same. So when you multiply a constant with the vector, the direction does not change, just the magnitude changes. But there's one situation. Now imagine let me go back to the original color, my yellow. Okay, so I have F and I multiply this with -1, and I get a new. So let me go back to my old colors, light green. So now F prime is in this direction. Magnitude of F prime is equal to magnitude of F, but the direction is exactly opposite. This is what multiplication with -1 does. Magnitude remains the same, direction changes to the opposite. Now next topic of relevance to spring is vector dot product. So I have a block of mass m, and a force applies on this block, and there is a displacement d, and the angle between those two is phi. So work is a dot product between two vectors, force and displacement, and we write dot product as a dot. It is different from multiplication that we had drawn earlier. So the value of work is equal to magnitude of force multiplied with magnitude of displacement and cosine of phi. So this is the definition of a dot product. So work is cos phi. Now let's look at three scenarios. Number one, phi equal to 0, force equal to 1 Newton, and displacement equal to 0.5 meters. So in this case, work will be 1 Newton multiplied with 0.5 meters multiplied with cos, and what is the phi? 0 degree. So this will become 1 multiplied with 0.5 is equal to 0.5 Newton meter. So this is almost simple product of two vectors. Now in the second case, phi is 90 degrees and force and displacement remain the same. So work will be 1 Newton magnitude of 0.5 meter multiplied with cos of 90 degrees, and we know cos 90 degree is 0. So it's 1 Newton multiplied with 0.5 meter multiplied with 0 is equal to 0. And let me draw this with a different color so that we know. So in this case, this angle was 90 degrees and this is my force. Now third scenario, in the third scenario, phi is 180 degrees. So we plug in the values again. 1 Newton, 0.5 meter multiplied with cos 180 degrees, and 180 degrees minus 1. So this becomes 1 multiplied with 1 multiplied with minus 1, sorry, is 0.5. Displacement is 0.5 multiplied with minus 1, so you get minus 0.5 Newton meter. So this is very similar to multiplying with minus 1, and you need to pay attention now. Work when the angle is 180 degree is negative, and we will revisit this again little later. When phi is equal to 180 degrees. In fact, will be negative when phi is more than 90 degrees. So, and in your head there will be a lot of questions coming because of what we have drawn here. See if I draw. See this whole area, for if the force takes any angle greater than 90 degrees, work done by this force will be negative, and we will look at it in more detail soon. Now next and the final topic in vector multiplication is the cross product. I want something more luminous. Okay. Cross product of vector. So take an example. This is your axle and this is a shaft. The let's call it length L of this shaft, and you have a force working on it in this direction. You can imagine, you know, a cycle bicycle pedal. So you are pushing it down. So the torque, which is a vector, is a cross product between the force and the arm, the length of the arm. So this I have just drawn the magnitude, but this tells you the direction. So if I were to plot this on a XY axis, this is what it will look like. This is the vector L, and this is the force F. So what will happen if you apply a force like this? This will rotate. So that's why torque is a vector. And this is a very important concept that I'm about to tell you. The direction of what happens in cross product. Magnitude of the torque is easy. It is magnitude of the force multiplied with magnitude of the length of the arm with sine phi. In this case, sine phi is 90 degree between these two. So the magnitude is same as force multiplied with magnitude of arm and sine sine 90 degrees, which is 1. Now let's look at what happens to the direction. And this time let me draw a 3-dimensional axis. So this is my X, this is my Y, and this is, so L is in this direction, F is along the Y direction, so it is in XY plane. So force and L are in XY plane. The torque will be in this direction, that is perpendicular to the XY plane. So if this is my XY plane, the direction of the torque will be perpendicular to this plane, and it's hard to depict when it's coming out of the plane. So the convention for cross product is like this. We use an arrow. So suppose this is a arrow and it has got the feather. So if the arrow is pointing at me, I will see it as a point, and when it is going inside the blackboard, I will see the back of the arrow. So this is coming out of the blackboard and this is going into the blackboard. So the concept for you to remember here, very important, that in cross product you get vector out, and torque is a vector. This is the magnitude of that vector, and the direction is perpendicular to the plane of the two vectors. So if you have XY plane and your force and the arm is in XY plane, the vector will be in the Z plane, which is perpendicular to this. So if the force was the way I have shown it here, in this case, by following the convention, the vector will be going in to the blackboard. So this direction will be going into the blackboard. So this is what we have covered in vector multiplication with a constant. So we saw the constant does not do much to direction. It can go in the opposite direction, but it basically changes the magnitude of the vector. In dot product, you get a scalar out of two vectors, and we saw that how if the angle is 0, the work done is like multiplication of force and displacement. If the angle between force and displacement is 90 degrees, work done by that force is 0. If the angle between force and displacement is 180 degrees, work can be negative, and we will look at it in little more detail. And this is the cross product of vectors. This is cross product of vectors, two vectors. of two vectors, you get a vector out. Now the next topic that we briefly saw when we were looking at the plane. So momentum and impulse. So momentum P is written as P is equal to mass multiplied with velocity, and both are momentum is a vector like velocity, and you can see that if I have a block of 5 kgs which is traveling with velocity 10 meters per second in a direction 30 degrees with the x-axis, so the momentum will be mass 5 kgs, velocity 10 meters per second at an angle 30 degrees with the x-axis. Impulse is rate of change in momentum, and this is very important. So if this object was traveling and it came to stop in 5 seconds, so momentum became 0 in 5 seconds. So impulse will be the initial momentum, which is 50 kg meters per second divided by 5, and that is seconds, that is 10 Newton. So as you can see, smaller the time, more will be the impulse, and impulse is same as the force. So if an object is traveling with certain momentum, and if you want to minimize the force of impact when you want to bring it to stop, you can put a delay. So if this was, say, 10 seconds, impulse would be 5 Newton, half of that. And now I will revisit this topic of work and force. And the last one is displacement. And this is very important. So I have a block of mass m, a force F worked on this mass, and as a result there was a displacement d, and the angle between these two is phi. So work This is not a vector, it's a scalar. So work is a dot product between those two, force and displacement. And we write this because it's a scalar, cos phi. Now imagine the force is in this direction and the angle is 180 degrees. So work in this case will become force multiplied with magnitude of displacement multiplied with cos 180 degrees, and this is minus magnitude of force multiplied with displacement. So if force is 1 Newton, displacement is 0.5 meters, work will be minus 0.5 Newton meter. Now you must be wondering that if the force is going in this direction, minus x, and displacement is in plus x direction, how is it possible that the block will move? Let me repeat. What happened in this case, force is in minus x direction, but displacement is in this in the plus x direction, and the work became minus 0.5 Newton meter. So what is happening is that there is another force in this direction, and call it F prime, which is larger than F, and that's why the block moved in this direction. So if I was to look at the perspective of F prime, work done by F prime is positive. Because cos phi, the angle, let's call this theta, because work is magnitude of F prime multiplied with displacement multiplied with the cos between those two, and this is cos 0. So this is F prime multiplied with d, and that's why it is positive. And that brings me to a very important concept called independence of forces. So if you have a block and there are many forces working on it, F1, F2, F3, and F4, F5, and F6. They all act as if they are independent of each other. This is it's not intuitive, but each force acts as if they are independent of each other. So that's why this F prime and this F, they were going in exactly opposite direction, and as a result, because F was smaller than F prime, the work done by F is negative and work done by F prime is positive. Feel free to revisit these sections and learn. And the last topic of prerequisites is energy. Energy. So energy, the definition of energy is ability to work. And there are two types of energies: potential energy and kinetic energy. So if you take a block here and you raise it up here by a height h, so the mass is m. At this point, the potential energy is mg h, and if the block is moving with a velocity v, the kinetic energy is half mv square. And let me tell you something very interesting. Let's do dimensional analysis of work and potential energy and kinetic energy. So dimensional analysis, we have three objects: mass, length, and time. So work is a dot product of force and displacement. So by dimensional analysis, force is mass multiplied with acceleration, and this whole thing is dotted with displacement. So mass is m, acceleration is L t raised to the power minus 2, and we multiply it with displacement L. So this is mass L square t minus 2 square. So this is work. Now let's look at kinetic energy. So it's written as half mv square. So dimensionally you have m multiplied with L t minus raised to power square. Half the constant is dimensionless, so this becomes L square. So this is my second, and let's look at example of potential energy, and we have a great example, m g h, mass. G is same as acceleration, which is L t minus 2, h is L. So this tells us that energy and work are interchangeable. Potential and kinetic energy are interchangeable. Alright, so we have covered, let me see. So we have covered these prerequisites: scalar and vector, Welter multiplication, displacement, force, momentum and impulse, work and energy. These are very important topic. These are the building blocks. And now we are ready to move into part 3, which is the main topic of this video. So we'll see you again shortly. Thank you.